Hello, my name is Fabio Tabacow, and I will present my work titled Theoretical and Experimental Study of Supersonic Gas Jet Targets for Laser Wakefield Acceleration. So first of all, I'll make a previous introduction for this work. The use of the laser acceleration system has grown rapidly in the scientific community as a new technology for particle accelerator system. And it reduces the size and complexity and consequently the cost of particle accelerators. Moreover, in this type of acceleration systems, usually renewable and fluid targets are used created the plasma and stimulated the generation of a longitudinal electrical wake field capable of accelerating electrons. The nozzle that can accelerate the gas jet in a supersonic flow are the level nozzles. That is this kind of nozzle here represented. They are convergent, divergent nozzles, and it's shown that. Because of this, we are working to implement a laser wakefield acceleration in our laboratory, which demands the use of this kind of gas jet laser targets to accelerate electrons. Here in this figure, we represented the Laval nozzles, and this side of this figure are the pressure, temperature, and density. Density of our gas system, and at this side the same properties here, but for the chamber, the vacuum chamber, the experimental chamber. Here's the throat radius, and here's the exit radius of the Laval nozzle. This is a homemade nozzle built in our laboratory, and it will be compared to a theoretical analysis made with computational dynamic fluids with a finite element method. The software used for the simulation is named as is version 19 academic. So a simple quasi one-dimension model can estimate the gas jet Mach number based on the ratio of the exit and throat areas, represented here in this equation. So this is the Mach number, and here is only this property of the gas used. This model disregards the exact value of the background pressure in which the jet expands, the presence of shock waves, and the nozzle length and length of the convergent region. To better understand this design model and the numerical simulation used by us in this work. So now I will talk about our methodology used here in this work. For the experimental results, we assembled a Mach number interferometer like this one. With Schillerian images, and to characterize the profile and the gas density in the jet generated by homemade nozzles. Here's a green helium neon laser that emit the beam, continuum beam, that is splitted here in this beam splitter. One of the arm of the of the beam have passed through the gas that is inside a vacuum chamber. Here is one lens that can that project its image in the CCD surfaces. So it is positioned 12 centimeters away from the jet, and that's it. This jet is positioned inside a small vacuum, like told by me, and this vacuum chamber has a Brewster window. The back-end pressure and the gas net is up to 50 bar, and the residual vacuum chamber is about 20 millibar. The CFD simulation is used to understand the flow and the phenomena that can happen when the gas is forced to a flow through a homemade level nozzle. It works. In this work, we simulated an etched nozzle in a 600 micra thick aluminum plate by an ultra short pulse machine system in our lab. The diameter of this nozzle are for the exit 190 and 86 micrometers for the throat. It defines a Mach number about 3 for nitrogen gas according to this quasi-static model. More details of this manufacture of the nozzle can be seen in the work of Bruno Kyometo titled Development of the Electric and Level Nozzles for Laser Electron Acceleration by Ultra Short Pulse Micro Machine that will be presented in these conferences. The fluid used here in this simulation, that's the results, is an ideal nitrogen in a CFX model of phases, and the gas flow is described by another Stokes differential equations. So these equations are solved using an upwind scheme discretization method, and the turbulence is modeled by the K epsilon method. The backend pressure and the background pressure is the same of the experimental, and in this, the background pressure is determined with an exhaust pressure like the background pressure of our experimental. So in the result session, we divided it in experimental analysis and theoretical analysis and a comparison between them. So in experimental analysis, the figure here presents the interferogram images acquired by the CCD, and this right shows the density map derived from an interferogram after applying mathematical method in these images. So from this density map here, we can measure the divergence angle of the gas jet and it's about 20, like here we can see it. According to this quasi 1D model, the Mach number is of this model. The Mach number estimated is about 2.8. The work presented by Armando Zuffi, titled Development of a Modified Mach-Zehnder Interferometer for Time and Space Density Measure for Laser Wakefield Acceleration, is possible to verify with more details the process to acquire the density map of by this interferometer. About the theoretical analysis here, as I already told, the nozzle was the same, has the same diameters and length as the experimentals. We consider that it has long hardness, and here in this figure, this figure is the Mach number distribution show, and it can see the maximum value here, and then it occurs near the exit of the nozzle. We can also see that it's about 2.5 number. So the discrepancy about the value and the experimental results come from simplified 1D model that disregards some real factors, for example, the length and the shape nozzles. So this figure shows the molecular density distribution on the gas in the gas jet in orthogonal planes. In this one, we can see an abrupt change. So that is desired for laser wakefield acceleration, and in this other figure here, we can see that it's possible to see that the jet has a circular section for the jet. The density decrease along the jet growth and minimize the value is reached as the exit and the increase. Some inhomogeneities in this figure, simulation artifacts based on a non-ideal discretization of the plane, of the space, due to an academic license that has a limitation of the maximum number of nodes and elements of the grids. These characteristics result in a simulation that does not describe exactly the physical system. When you have a limited number of elements, the simulation volume needs to be small, but keeping large enough to minimize the wall interferences. The number of the element influences the spatial resolution because it influences the size of the elements. Another fact that is responsible for those discrepancies in the background residual pressure due to an exhaustion that was modulated to extract the gas from the vacuum chamber. This residual pressure limits the expansion for the gas. So comparing the experimental and theoretical results is possible to verify here. Comparing this both figures, that the jet behavior is closely. So mostly the Mach number and density close. for the nozzle exit about 100 micrometers away. Although the experimental jet is more divergent than the theoretical prediction. The Mach number difference is due to models used. So here we simulated, and then this one we can we use these models here. So we concluded in this work that the simulation model described the experimental results of the jet flows fairly close, but more studies need to be improved to get more realistic prediction and design better nozzles and gas targets. With the knowledge that we are acquiring in this study, it's possible to perform simulation of more complex systems in the future. So I would like to thank the financial support from FAPESP, CNPq, CAPS, and the CNPq scholarship to ZUFI and for me. So thank you